Hi, everyone. My name is Liz Watkins, and I have the privilege of serving as the Dean of the Graduate Division at UCSF. And I want to welcome you to these 2018 Discovery Talks. This event is the signature event of the Graduate Division at Alumni Weekend. And I am so excited for you to hear from this year's lineup of speakers, so my introductory remarks will be very brief. As you all know, our faculty members are engaged at the forefront of biomedical inquiry with research on topics that range from molecules and cells to individuals and populations. And so the aim of these discovery talks is to give you a taste of the exciting research that's taking place at UCSF right now, which allows us to attract the very best PhD students and postdocs to come here to work with our talented faculty. The mentor-mentee relationship is mutually beneficial at UCSF. Students and postdocs learn side by side with world-class scientists and scholars, and in turn, those scientists and scholars get the benefit of a highly skilled team that help them to carry out their research. Graduate students and postdocs are the engines that drive the research enterprise, contributing to the discovery and the innovation that are the hallmarks of UCSF. And so, let's get on with the show. The plan is this. The speakers will make their presentations one after the other with just a short introduction from me in between each talk. I'll ask you to hold your questions and comments until the end. The speakers have all planned to stay after the program to chat informally with anyone who wishes to talk to them. And so, to begin, our first speaker is Dr. Jeremy Reiter. Jeremy is a graduate of our medical scientist training program, which is UCSF's dual degree MD PhD program. He currently serves as the chair of the Department of Biochemistry and Biophysics after having served for several years as the program director for the PhD program in Developmental and Stem Cell Biology. His lab studies primary cilia, the small antenna-like structures present on nearly all cell types, and the title of his talk today is Cilia Are Your Cells Antennae? Jeremy.
So my job here is to tell you a little bit about the research that I'm doing here at UCSF and the kind of exciting basic biology. But my meta message is that UCSF is a wonderful place that a lot of you guys know about, where you can study something as seemingly trivial as cilia and maybe make kind of surprising discoveries that could impact human health within our lifetimes. So most of you probably are familiar with cilia from 6th grade biology, where you studied pond water through a microscope and you saw paramecia floating around, and they use these cilia in order to be able to swim and find their food. So lots of organisms have cilia, and we have motile cilia too. So right now you've got motile cilia in your lungs that are busily moving the mucus and gunk that you've breathed in out of your lungs. But those aren't the only cilia. I'm actually interested in the non-motile cilia, and you're using your non-motile cilia right now too. So at the back of your eye, you've got your photoreceptor cells, and if you remember your histology, there's this weird thing called an outer segment, and that's where your opsins are receiving the photons that are bumping off of me and recreating an image of your external world. And that outer segment is just a highly modified cilium. Structurally, it looks very similar to those cilia that are on the paramecia that are moving that paramecia around. So evolution over the last 4 billion years or so has obviously utilized this structure for very different purposes. And so there are cilia on paramecia. That's not what I'm interested in. There are cilia on the back of your eye. That's not what I'm interested in. So what am I interested in? Well, it turns out that these so-called primary cilia, these non-motile cilia, exist on almost every cell in your body. So cells in your teeth, cells in your brain, your neurons in your brain, cells in your skin, almost everything except for your blood can have this single immotile projection off the surface of the cell. And even 10 years ago, you could find textbooks that said, oh, this is probably a vestigial organelle, kind of like your appendix. It probably doesn't do anything, but evolution, it just never got rid of it or something like that. So one of the advances from my lab has been to try to figure out, is that true? Do these things not really do anything on all of these cells in which they exist? And I'm here to tell you that that's not true, that we're going to have to revise Bruce Albert's textbook in the next edition and say that the cilium is in fact packed with machinery involved in not sensing light from the outside, but sensing cues from other cells. So one of the signaling machinery pathways that is housed within this antenna is for an intercellular cue called hedgehog. Originally discovered in Drosophila, that's where it gets its name, but you and I have 3 different hedgehogs, and they do important things. So for example, you have 5 digits in your hand because of hedgehog cues during development. And your thumb is your thumb because it got high levels of hedgehog, and your pinky is your pinky because it got low levels of hedgehog. And when we disrupt cilia in, say, a model organism like the mouse, then we disrupt the ability of those cells to receive that cue, and thus we disrupt the number of digits and the identity of those digits within the limb bud. So the cilia on those cells are packed full of machinery that is involved in receiving those cues that have important roles for all sorts of developmental events when we're in utero. And consequently, working with human geneticists like Ophir, we've been able to identify genes in rare families that cause defects that result in developmental disorders in humans called, for example, Joubert disorder, in which polydactyly is one of the hallmarks, but other hallmarks include cysts in the kidneys and problems in the brainstem formation. So these kids have kind of a range of different developmental defects, and this has led to this idea of ciliopathies as a class of human diseases. This class of diseases that don't have hallmarks akin to each other, but that are all caused by defects in the form or function of these antennae, these primary cilia. So Joubert happens to be one of kind of the rarer classes of these ciliopathies, but it turns out that there are more common ciliopathies called, for example, polycystic kidney disease. Polycystic kidney disease is a problem in cyst formation in the kidneys, and this is a disease that is actually a really important human disease. It doesn't get a lot of love, but it's more common than cystic fibrosis, it's more common than sickle cell anemia, it's more common than Down syndrome, it's actually more common than all 3 of those combined. It's the most common monogenic inherited disorder in humans. And we really don't have therapies for this, but those cysts are caused by defects in these antennae, not receiving hedgehog, but a different cue that is transduced through 2 different proteins that sit on this antenna called PKD1 and PKD2 for polycystic kidney disease 1 and polycystic kidney disease 2. So there's a strange organelle that's on paramecia, but it's also on all of our cells, that's involved in receiving cues from other cells, both during development and in you and me. So kind of the cutting edge right now within my lab is to say, well, okay, there's this class of ciliopathies that are directly attributable to defects in this antenna. Could these antennae also be doing things involved in much more common diseases, diseases that we don't typically think of as these ciliopathies directly attached? But if it's this organelle that's important for all sorts of intercellular communication, then maybe it's doing things in other types of diseases, such as aging and cancer. So one of the things that we've been very much interested in is whether cancers can be ciliated, and it turns out that they can. So basal cell carcinoma is the most common cancer in North America, and if the camera zooms in on the tip of my nose, you'll see a little scar where my dermatologist whacked off a basal cell carcinoma from the tip of my nose. And it turns out that this is one of the cancers that is ciliated. And it turns out that using genetic models in the mouse, we can show that if you remove those cilia from those cancers stop being cancers. So can we use this insight to gain novel insights in how to treat these cancers? Basal cell carcinoma, I apologize to any dermatologists out there, is not the cancer that I want to devote the rest of my life to. Most dermatologists can whack them off pretty easily. If you're going to get cancer, basal cell carcinoma is probably the cancer you want to get. But it turns out that there's another cancer called medulloblastoma. Medulloblastoma is a nasty brain tumor. It affects children. It's the most common solid cancer in children. There are therapies, but the therapies that currently exist leave children devastated, so profoundly intellectually disabled for the rest of their lives because the therapies involve total neuraxis irradiation. It turns out that medulloblastoma is another one of these cancers that uses this cilium in order to get this grow signal. And so the current work within my lab is understanding how the machinery at that cilium works and whether we can use novel pharmacological approaches to block that oncogenic signaling at the cilium.
Thank you, Jeremy. Our next speaker is Dr. Maria Gleamore. Maria is an associate professor in the Department of Epidemiology and Biostatistics, and she also serves as the director of the PhD program in Epidemiology and Translational Science. Her research focuses on how social factors influence cognitive function and other health outcomes in old age. The title of her talk today is Causation, Correlation, and Why We Don't Yet Know How to Prevent Alzheimer's Disease. Maria.
Thank you. So it's a tremendous pleasure to be here. Thank you all for joining me. I felt like the last talk was kind of inspiring, and I'm going to start off on maybe some rougher news. I'm going to talk about statistics and Alzheimer's dementia. Alzheimer's dementia really looms as one of the most important epidemics of our time. If you live to age 65, there's about a 1 in 3 chance that you will develop dementia, and the most likely cause will be Alzheimer's disease. Alzheimer's disease is characterized by progressive and profound memory loss and confusion, and that loss often leads to a loss of identity, a loss of dignity, and a loss of the ability to connect with our loved ones. It's no surprise that there's profound interest in identifying ways to prevent and to cure Alzheimer's dementia. Unfortunately, we are making startlingly little progress on Alzheimer's disease. It's not that we're not trying. Between 1982 and 2012, there were over 400 randomized trials of new medications to treat Alzheimer's. And indeed, we had 5 new drugs approved. Unfortunately, those drugs had at best transient, small benefits for symptoms. They were nowhere near a cure. And since 2003, no new medications have been approved. Pfizer recently announced that they are giving up internal efforts to develop Alzheimer's drugs because the expense is just too much and there's no successful strategy in sight. So why has this been so challenging? It seems like compared to some of the other diseases where we are making phenomenal progress, we're sort of stuck with Alzheimer's. Even though there's sometimes great sounding press, the reality is it never presents compelling evidence about how to treat or cure how to prevent or cure Alzheimer's disease. I'm going to talk about 3 challenges in this research. And this is where we go back to statistics. And I think that by addressing these challenges, we can do better. The first challenge is measurement. It turns out it's very difficult to measure Alzheimer's disease. So if you look up at the slide, there's a picture of a PET amyloid image. And at the top is a PET amyloid image from somebody with normal cognition. And the middle is borderline. And the lower image is somebody with Alzheimer's disease. So amyloid is basically the hallmark neuropathologic characteristic of Alzheimer's disease and has been since Alzheimer's was first characterized in the early 20th century. Unfortunately, amyloid does not correlate perfectly with what we consider the most important symptom of Alzheimer's, memory impairment. So many people who have amyloid in their brain do not appear to have cognitive impairment. And many people who we diagnose with Alzheimer's based on their symptoms, memory impairment, they turn out not to have severe amyloid in their brain. What's going on? Why is there a disconnect such that people with what we think of as the major hallmark of Alzheimer's, many of them will have normal cognition throughout their lives and die of unrelated causes? We believe the reason is that there are multiple neuropathologic processes that combine and accumulate over decades to culminate in what we call Alzheimer's disease. We do not know how to measure each of those processes, unfortunately, and therefore we can't study them as well as we'd like. So that's problem number one, is the challenge of measurement. Problem number two is that we tend to think of Alzheimer's disease as a disease of old age. That is probably a mistake. Alzheimer's disease is probably better conceptualized as a life course disease, which starts early in life and continues on. Although there are many risk factors that we've identified in old age. So for example, doing crossword puzzles, social dancing, these are factors that predict lower risk of Alzheimer's disease. Having depression, stroke, these are factors that predict higher risk of Alzheimer's disease. But there are also many risk factors that appear to be more relevant in middle age, things in your 40s and 50s and 60s. So for example, hypertension, obesity, diabetes, even characteristics of the work you do predict your subsequent Alzheimer's dementia risk much later. We can even move earlier. It turns out that education is one of the most robust predictors of dementia. People who can complete more education and people who probably complete a more high-quality education have lower risk of dementia. We can even move earlier and think about knowing where you're born tells me something about your subsequent dementia risk. We did a study in a population of people who lived in Northern California for at least since the 1970s. And we showed that people who were born in places that had higher stroke risk, and if you look at the map up here, you can see where the deep purple is, those southeastern states, they have much higher stroke burden. People who were born in those places had dementia risk all these decades later, even though they had lived in Northern California for decades. So people were carrying that with them their whole lives. So when we look at late life and we look at memory and a disease in late life, we're probably looking at the culmination of things that have occurred from really conception through old age, some of which increase your risk and some of which decrease your risk. And it turns out that some of the most important opportunities for prevention may be occurring earlier in life. And if we only start our studies in late life, looking at late life factors, we miss the boat. We miss important opportunities. So that's problem number two. Problem number three is really the biggie, correlation versus causation. Probably and hopefully many of you out there raised your eyebrows a little bit when I said education predicts lower risk of dementia. Is that causation or is that correlation? Maybe it's just that, hey, really smart people get a lot of education, and it's the being really smart that protects you against dementia, not the education per se. Well, that is a big problem, because that study design is not just what we use for education in dementia. We use the same study design for almost everything that we study about dementia prevention. We look essentially at correlations. Now, we have a lot of other names for the correlations because we can do great stats. We have very glorified correlations, but essentially, we're saying, hey, is there a correlation between hypertension and Alzheimer's risk? Is there a correlation between diabetes and Alzheimer's risk? These have exactly the same challenges as looking at the correlation between education and dementia risk. We simply cannot establish the causal direction, whether it goes one way or the other. Now, if education were a drug, this would be simple. We would run a randomized controlled trial. We would randomly assign half of our participants to receive the PhD pill, or maybe the MD PhD pill. And we'd assign the other half of the participants to the high school diploma pill. And then we'd follow everybody for 50 years and see who gets Alzheimer's. We need a little bit of statistical machination, but when we do that, we'd be able to say, if you wait half a century, we know whether the PhD is actually protective against Alzheimer's. This is slow, expensive, and for many of the most important risk factors, probably unethical. So we have two options here. One is a correlational study, which we can't use to establish causal direction, but we can do quickly. And the other is a randomized control trial. Large, slow, expensive, not ethical. Are there any better options? The answer is yes, there is a better option, but we have to be a little bit more clever about how we design our studies. We have to think, instead of running a regular experiment, we can look for natural experiments. things that influence your exposure but have no other reason to be related to your Alzheimer's risk. For example, for education, one of the things that shapes how much education people get and the quality of education is where they go to school, where they live when they're going to school. We can show that people who are born in places that require longer schooling and provide higher quality of schooling actually have better memory when they get old, ages 60, 70, 80, and lower dementia risk. So that approach is a similar idea we can use to use genetic variants that influence obesity and diabetes to evaluate whether obesity and diabetes are causally related to Alzheimer's disease. This approach is really not the traditional correlational study. It takes advantage of what has been a statistical revolution in the last 30 years. Now, the statistical revolution you hear about the most in the press is probably about building machine learning algorithms to build beautiful prediction models. And those prediction models help us tell who's going to buy a new pair of tennis shoes, or whether this is a picture of a cat or a picture of a car. Fabulous machine learning algorithms. There has been a quieter, and I would argue more powerful revolution in causal thinking, in thinking about how we link large data sources to causal inferences. And understanding those causal structures is what will guide us to understand whether education, hypertension, obesity actually protect us against Alzheimer's disease. This new approach, this is actually a great time to be undertaking this new approach because those most rigorous methods require large data sets. They require large data sets that include information not typically linked. For example, schooling policies and dementia diagnoses. And so the new data that is now coming online really presents a new opportunity to drive better and more innovative study designs to identify the causal structures driving Alzheimer's disease. And it is those causal structures that we need to understand how to intervene to prevent and cure Alzheimer's and move to a world where we can all forget about Alzheimer's disease. Thank you.
Thank you, Maria. Our next speaker is Dr. Jennifer Grandis. Jenny is a professor in the Department of Otolaryngology, and she's affiliated with the Biomedical Sciences PhD program. She is also the principal investigator of UCSF's multi-million-dollar Clinical and Translational Science Award Program, a network of initiatives to strengthen and streamline clinical and translational research on campus. After many years as both a basic scientist and a head and neck surgeon, she's currently focusing on the development of effective preventive and therapeutic strategies for head and neck cancers. The title of her talk today is An Aspirin a Day. Jenny.
Thank you. Hello, everybody. It's really wonderful to be here, although neither my husband nor I had the opportunity to attend UCSF. We just work here for the last few years. We're really proud that our daughter is going to move here next month to go to medical school. So I went to medical school because I wanted to help people. And I became a head and neck surgeon because it gave me the illusion that I actually could cure people. There's something bad, I can cut it out, I can put the people back together, and they can go on with their lives. But what I learned during the first 10 years of my training and my faculty practice was, despite my exceptional technical skills and the efficacy of radiation and chemotherapy, half the patients still died of their primary head and neck cancer, and the rest of the population who survived their initial head and neck cancer were bound to die of a second malignancy of the throat or the lungs or the esophagus. And it was awful, and it occurred to me that I needed to do something else besides operate on people in order to help them. And that's what motivated me to become a scientist, because I understood clinical medicine. So the dream of being a translational scientist, or the hope I should say, is that someday you'll understand something about your patients and their disease clinically and scientifically that will enable you to put these two worlds together and come up with an innovative strategy. The hope, of course, is that this strategy is not toxic and that it's inexpensive. So I'm going to tell you such a story. So what we know about head and neck cancer in the United States is it's actually an epidemic. You've all heard of the human papillomavirus, and last year, the number of throat cancers related to human papillomavirus in men passed for the first time the number of cervical cancers in women, which we know are caused by human papillomavirus. And because those of us of a certain age did not get the HPV vaccine before we were exposed to the virus, this trend is just going up and up. What we know about these cancers is that they are filled with genetic alterations. So the promise of precision medicine, if you will, is that we can unravel the genetic characteristics of an individual tumor, and based on our understanding of biology and available drugs, is we can ideally identify the right drug for the right patient at the right time. So about 4 years ago, I was reading the New England Journal of Medicine, because I'm married to a cardiologist, and noticed that there had been this epidemiologic study. So it's a perfect segue from Maria's talk. And in this epidemiologic study, it was noted that individuals who had colon cancers that harbored a specific mutation, it's in an oncogene called PIK3CA. It just happened that if the tumor had a mutation and the individuals happened to be taking aspirin, they had significantly improved outcome. Nobody knew why. It was correlation. Nobody had any idea what the aspirin had to do with protecting these individuals from death with these individual tumors. So one of the great perks of being a physician scientist is that I understood this biology. We read this article and I'm like, oh my goodness, I've been studying the signaling pathway for a very long time, and we had just unraveled the genetic code of head and neck cancer, and it turns out that the mutations in this gene are the most common mutations in head and neck cancer. So 2/3 of patients with HPV-positive head and neck cancer have a mutation in this gene. And about 1/3 of patients whose tumors are caused by smoking have a mutation in this gene. So it suddenly becomes a really big population. So what we did is we had a cohort of patients because we had a grant to collect these patients. We had all the information about the drugs that we took, and I had their tumors. So we went and we sequenced these tumors. This was about 300 tumors. And lo and behold, it was a Hail Mary hypothesis, but it was remarkable. It turns out that if you have a head and neck cancer and your tumor has a mutation in this oncogene, your survival is worse. And that's not surprising. This is true for patients with colon cancer and breast cancer. Most patients whose tumors have a mutation in this oncogene have worse survival. Now, if your tumor did not have an alteration in this gene, and you happen to be taking NSAIDs, and our retrospective cohort, about 80% of the patients were on daily baby aspirin, probably for cardiovascular protection. It didn't matter. The survival was exactly what we would expect at 5 years, about 50%. However, if your tumor has this mutation, remember it's about 50 to 60% have this mutation, and you happen to be taking baby aspirin, your survival at 5 years went from 20% to 80%, which is remarkable. So suddenly, there's the possibility that I can see a patient with a lethal malignancy, and instead of taking away their ability to swallow or speak or disfiguring their face, I can give them a baby aspirin, and they might actually have an incredible outcome. So at the end of the day, we've unraveled the mechanism, the paper is in press, and we're now designing 2 more prospective studies. One study will actually look at the immune system, because the idea that this is so protective of death and it's not involving the immune system is ludicrous, and we have lots of reason to believe that this is true. So we're going to look at the impact of patients with cancer, head and neck cancer. We're going to give them, actually we can't give them aspirin because of bleeding, but we'll give them a celecoxib 2 weeks before surgery. We'll take out their tumor, and we'll look at the immune system. And the second will be a randomized placebo-controlled trial, so we can finally take patients after they've had their definitive therapy. Half the patients will get a baby aspirin, half the patients will get a placebo, and in 2 years we'll have those answers. So I'm cautiously optimistic that for the first time in my relatively long career, the promise of precision medicine is actually looking quite hopeful. So thank you very much.
Thank you, Jenny. Next up is Dr. Affair Kleine. Ophir is a professor in the Department of Orofacial Sciences, and he serves as director of the program in craniofacial biology in the School of Dentistry. He's a member of several PhD programs, including BMS, DSCB, OCS, and PSPG, which, for those of you who are not fully conversant with the alphabet soup of acronyms in the graduate division, are Biomedical Sciences, Developmental and Stem Cell Biology, Oral and Craniofacial Sciences, and Pharmaceutical Sciences and Pharmacogenomics. His lab studies how organs develop in the embryo and how they renew and regenerate in the adult. And the title of his talk today is Developmental Biology as a Blueprint for Regenerative Medicine. Ophir.
I want to thank Dean Watkins and the development team for the opportunity to speak with you. Organ failure is a central problem in aging, and one that many of us will suffer greatly from and even succumb to. And one of the hopes is that in the long run, we will be able to create organs in order to replace those that fail. Hearts, livers, kidneys, eyes, teeth, virtually any organ is prone to failure as we age. And the dream of regenerative medicine, what you might call the fountain of youth, is to be able to fix organs when they fail or even before. Unfortunately, we don't have great medicines yet to fix failing organs, and we don't have enough organs available for transplant, so many patients die because of this. Also, those of us in pediatrics know well that many babies are born with structural birth defects, malformed or missing organs. So fortunately, nature has given us the perfect building blocks that we can use in order to begin to solve this problem. And what I want to share with you today is this idea that I put in the title of my talk, that developmental biology principles can serve as a blueprint for regenerative medicine. In our lab, we're interested in understanding how organs form in embryos and how they regenerate in the adult. And we study these processes in a number of organs, including those shown on this slide, 3 components of the craniofacial complex, the tooth, the tongue, and the lining of the inside of the mouth called the oral mucosa, as well as the intestine. And the hope is that by understanding these basic processes in development, we can begin to make replacement parts for patients in the long run out of their own cells. Understanding these fundamental principles is thus not only a really fascinating basic science question, but also really key to being able to help patients in the long run. So I want to share a couple of different scenarios with you that we've been thinking about. Number one is, how can we boost a patient's own stem cells, the endogenous stem cells that are present in the body, in order to fight and protect against disease? And number two, how can we use principles of developmental and stem cell biology in order to think about making tissues, parts of organs, or even entirely new organs? So the approach that we've been thinking about for boosting patients' own stem cells, their endogenous stem cells, involve both prenatal and adult studies. In terms of the adult, we've been looking at the intestine, which is one of the most regenerative tissues in the body, and its lining turns over every few days. Now, work done over the past several decades has taught us much about the stem cells that drive this renewal, this constant turnover, including where the stem cells that enable renewal reside, what signaling molecules and growth factors drive this renewal, and how the stem cells respond to damage. So this then now provides us with an opportunity to harness the power of these stem cells in order to help patients. And we've been thinking about these in conditions like inflammatory bowel disease, in which patients suffer greatly from fatigue and weakness, inflammation, and these can lead to severe complications and even become life-threatening. So what we've been thinking about is, how can we use molecules that tell the patient's own stem cells to become more active and to protect against the disease? And using animal models and now thinking about how to move this into patients is actually showing great promise. Another exciting example in this area is a recent clinical trial that we participated in, which is for a condition known as XLHED, which I know is a mouthful. This stands for X-linked hypohidrotic ectodermal dysplasia. And what happens in this condition is that the ectodermal appendages, which are organs like the teeth, hair follicles, sweat glands, mammary glands, do not form properly because a single protein is missing. So at UCSF, we were fortunate to participate in the initial clinical safety and efficacy trials to give back this missing protein to patients. And I'm very excited to tell you that our colleagues in Germany just reported a few weeks ago in the New England Journal of Medicine that by providing this missing protein to affected fetuses prenatally before they're born in the mother's womb, it's possible to cure many aspects of this disease. So this is a particularly exciting trial because it represents the first successful attempt to treat structural birth defects with a medicine instead of with a surgery. If you think about all the structural birth defects that we encounter, cleft palate, bone anomalies, heart defects, kidney defects, all of these require surgeries to treat them. And here, by using the knowledge that's based on this fundamental understanding of development, we're able to really shift the paradigm and use a medicine, a drug, instead of a surgery to treat patients. So perhaps even bolder than giving missing proteins to fetuses before they're born is the idea of making replacement organs. One area that we've been really interested in is tooth regeneration. As I'm sure you're all aware, there are millions of people around the world who suffer from missing teeth, teeth that degenerate, have severe caries, diseases of the gums and lining of the mouth. So there's great need in this area. But another reason that we became interested in this is because tooth regeneration actually provides a great model for understanding how we can think about making new organs. Unlike organs such as kidneys or livers or hearts, if we put a regenerated tooth into the mouth of a patient, if that tooth fails, while it would be problematic, it wouldn't be catastrophic. So by using fundamental principles from development, including understanding the growth factors and signals that drive the formation of the organ, we can then use these ideas in order to think about how to make new teeth. And while we've learned a lot over the past few years, there's still a great deal that we need to learn. And our hope is that by combining this growing knowledge with the work of our colleagues from bioengineering, we can integrate cells into scaffolds and add the proper nutrients. And then this will eventually lead to our ability to grow new organs, which I know it sounds like science fiction, but actually it's work that's ongoing in the lab right now. Another approach that we've been taking to trying to use developmental and stem cell biology principles for organ regeneration is to learn from nature. Because there are many species of animals that are able to grow their teeth continuously throughout their lives, unlike us humans who don't have that ability. And this ability to grow teeth continuously has independently evolved in multiple species. If you think about elephants and walruses with their tusks, or any of you who have pet rabbits at home and have had to repeatedly take that rabbit to the vet to get its trimmed teeth, know that rabbit teeth grow continuously as well. By understanding how these stem cells arose during evolution and how they function in other species, we can then harness and adapt these powers that exist in other animals in order to think about how we can use them for humans as well. And so the message that I want to leave you with today about this idea of using developmental biology in order to understand how we can lay a blueprint for regeneration is that those abilities are actually out there, and all we need to do is harness them. So I think the future is incredibly bright with enormous promise for this idea of using development as a blueprint for regenerative medicine. Thank you.
Thank you, Ophir. Our fifth speaker today is Dr. Monica Macklemore. Monica is an assistant professor in the Family Healthcare Nursing Department, and she's affiliated with the Nursing PhD program. She's a clinician scientist at Advancing New Standards in Reproductive Health, which is an affiliated member of the Bixby Center for Global Reproductive Health. And if that weren't enough, she's also a staff nurse at Zuckerberg San Francisco General. Her research on women's reproductive health and justice aims to improve patient outcomes, improve access to care, and improve patients' experiences with their care. The title of her talk today is, What is Reproductive Justice and Why Does It Matter? Monica.
Wow, this is an incredible room, and how exciting it is to be here with all of you. I'm going to start with a quote and end with a list. So I'll start at the podium, and then I'll move. I'm going to walk you through 3 dates: 1906, 1969, 1994. In 1906, the national black leader W.E.B. Du Bois, the father of modern sociology, challenged the bleak forecast of inherent black inferiority. In a report entitled The Health Physique of the Negro American, these were proceedings drawn from an Atlanta conference on black health. Commenting on the higher black rates, Dubois noted that the present differences in morbidity and mortality seem to be sufficiently explained by the conditions of life. In my mind, this was one of the first descriptions of social determinants of health. I was born a preemie in 1969, 12/31/69. My birthday was actually supposed to be February 14th of 1970. At that time, I was born in Trenton, New Jersey, and the infant mortality rate for the entire state was 20 out of 1,000 infants. For white people, it was 16.3%, or 16.3 per thousand, and for all other races, because they didn't distinguish them, it was 35.7 per thousand. I am both grateful and lucky to be alive. As a preemie, it's been very interesting for me to be able to think about how could we redesign reproductive health, rights, and justice. So you've heard 1906, you've heard 1969. In 1994, a group of radical black women coined a term called reproductive justice. And they made a clear distinction between reproductive health, reproductive rights, and reproductive justice. As a nurse, I provide reproductive health services provision. Our lawyers, our advocates, and people who fight on our behalf every day for reproductive rights exist in that space. However, reproductive justice is a very different thing, and it's different because it's predicated upon 4 very simple principles. The first is you have a human right to be able to become pregnant, to be a parent, to be able to do that with dignity, and to have the things that you need in society in order to be able to be successful. You have a right, a human right, not to become a parent, and to have the things to keep you from not becoming a parent if you so choose. You have a right to be able to parent with dignity, safe from violence, both from individuals and from the government. And the last tenet is you have the right, the human right, to be able to disassociate sex from reproduction. This simple framework is radical when you think about it because it encompasses many things. I'm really proud to be a UCSF alum, and in 2015, I was granted the Hellman Family Fellows Fund Fellowship to be able to conduct some very important work to study black and brown women in Oakland, California, at multiple time points during pregnancy, to ask them about their stress, their resilience, their coping, their assets. And our data were not surprising. It was a highly stressed group of women, highly resilient group of women. Later on that year, I conducted some qualitative interviews and focus groups with the UCSF Preterm Birth Initiative, which is a multi-year initiative really trying to turn the needle on prematurity. And in San Francisco, Oakland, Fresno, we collected data out of 7 different focus groups in English and Spanish, 54 women, 2 hours each, twice, asking them about their experiences of their care, asking them about what we could do to be better clinicians and partners in their care. We published our data in Social Science and Medicine because we really, really wanted to bring forward the important findings from our study. Our participants told us about disrespect. They told us about not being believed. They told us about not having their clinical care team be able to recognize signs and symptoms of deterioration. They talked about racism. They talked about discrimination. While all of that was going on, Nina Martin from ProPublica and Renee Montaigne from NPR launched an incredible journalistic endeavor called the Lost Mothers series. They won a Peabody Award and they became finalists for a Pulitzer Prize because they really wanted to raise awareness around the tragedy, the shameful fact that maternal morbidity and mortality in the United States is actually worse than when my mother gave birth to me prematurely in 1969. That prematurity was rising over the last 3 years. That maternal morbidity, the burden of maternal morbidity lives with Black women, who are 3 to 4 more times likely to die from a pregnancy-related problem in the United States in 2018. So one of the things that I think is most important for us to understand is it doesn't have to be like this. I'm a really, really big fan of top 10 lists. Before I tell you how I think we should redesign health services provision, reproductive rights, and get to a reproductive justice vision, I want to talk to you about the GOAT. The GOAT is the greatest of all time, Serena Williams. In January of 2018, she told her first-person narrative to Vogue magazine, and here she is on the cover of Vogue with her daughter, Alexis Olympia, her first child. Serena Williams was born in 1981, and I specifically tell you this because I was born in 1969, and because Blackness affords us youth when you see us, I like to be able to distinguish, not only was she a very young mother, not only is she one of the most fit and elite athletes of our time, 39 Grand Slams. This is a person who went into an uneventful pregnancy, despite the fact that she has known health issues, including a clotting disorder that renders her vulnerable to blood clots. But this is a person who makes their entire living and fortune, who is rich, Black, young, and pregnant, and had to talk her entire healthcare team, nurses, physicians, other clinicians, into how to take care of her when she was having her birth and her postpartum period. If you don't know the story, she ended up having blood clots and she had a dehiscence of her C-section wound that required an additional surgery that left her in bed 6 weeks after she delivered her daughter. She also penned a first-person op-ed for CNN talking about the systemic changes that we need to make in terms of how pregnancy care is delivered in the United States. So with her words, with her thoughts, I want to leave us with a way forward. How would reproductive justice change how we would design health services provision? I'm a big fan of David Letterman, and so I'm going to do this top 10 list style. Number 1, we could redesign care such that paid family leave becomes the norm in the United States, that a basic minimum income is provided to citizens, because I worry that we are becoming a country where poor people are unable to parent with dignity, that immigrant children are not separated from their families, and that we can figure out, because we have the brilliance, to stop incarcerating pregnant people. Because I think it's unethical for babies to begin their lives in jail just because their parents committed a crime. That maternity coverage does not continue to be discussed as an optional coverage on healthcare exchanges as we discuss the Affordable Care Act and whatever replaces it. That Title X be fully funded to provide access to family planning, contraception, and abortion services. That we not only understand the need for abortion within the context of reproductive justice, but we understand that it has quality and safety as outlined by the National Academy of Science and Engineering and Medicine recent report. That we know that in states that expanded Medicaid, pregnant people and infants have a better short-term outcome, and that it's unethical to deny the expansion of Medicaid and to deny coverage when we know that intervention alone improves population health. That doulas can be provided, people to provide informational and spiritual support to individuals during pregnancy, and that a midwifery model of care should be expanded. The other thing as a university I want us to agree around is that our future patients and the public that we serve should be looked upon as our future workforce. In closing, what is reproductive justice? It's a roadmap and a human rights framework to maximize the gifts and talents of the human species. It's a set of human rights principles that allow people, particularly women, to fully participate in society. And why do we need it? Because in the 48 years I've been alive as a Black woman on this earth, health outcomes for people who look like me have not improved. And quite frankly, I know we can do better, and this can all be different. I hope you'll join me in imagining a new future. Thank you.
Thank you, Monica. Our final speaker this morning is Dr. Beau Wong. Beau is a professor in the Department of Pharmaceutical Chemistry, and he is affiliated with 5 PhD programs: bioengineering, biophysics, biomedical informatics, chemistry and chemical biology, and our tetrad program. His lab develops techniques in light microscopy and uses these techniques to study fundamental questions in cell biology. Beau was chosen to give the prestigious Byers Award lecture in basic science this year. The title of his talk is Watching the Inner World of Life. Beau.
Okay, yeah, it's a really great honor and big pleasure to be the very last speaker for the Discovery Talks. And I'm sure you have enjoyed talks about topics ranging all the way from the tiny, small cilium to the entire big human society. And so here as the last speaker, I'd like to put everything into perspective of size, or in bigger words, than scale. Well, you know, our human body is about the size, well, scale a meter, and inside our body, the organs about decimeter, the tissues, centimeter, millimeter, talk about. Then, if we want further zoom in to the fundamental unit of life, the cell, it's a lot smaller. It's about 200 magnitude down, and that's about 20 micrometer. And to make it more visual, it's about a quarter of the size of a diameter of a hair. So that's how small the cell is. I call it, well, it's small, and I call it the fundamental unit of life. It doesn't mean that the cells are solid squishy balls and our human body just piled up by a whole bunch of solid squishy balls. That's not the case. The cells has extremely complex structure inside, which I call the inner world of life. The cells have organelles like the cilium, and that's the antenna of the cell, the mitochondria, that's the powerhouse of the cell that generates all the energy that we can walk and we can think. And the cells have the chromosome that's made of DNA and proteins that contain all the genetic code that determines what are us and who are us. And they are also in big complex made of many proteins and nucleic acid, like the ribosome. That's the machine that translates this genetic code into the proteins that builds up the whole cell. And if we want to further zoom in all these structures, these machinery that are made of molecules, the proteins, nucleic acid, and they are about the size of a few nanometer, and this is like hugely small. And there are small molecules that's the size of angstroms. That's the resolution we need to describe the structure. So all these things span a huge scale of length. If we compare, like say, a human being to the size of the Earth, and then a cell would be about the size of this stage in the entire Earth. And then we talk about the size of a protein molecule. That would be about my fingernail compared to the stage and compared to the entire Earth. But for many of the disease, it's exactly those things going wrong at the small molecular scale. And for example, we've heard that some cancer are caused by genetic mutations. It's actually just like a few atoms changed on the DNA molecule, a 1 hydrogen bond change that caused the genetic code to change. And the ribosome will interpret that into a different amino acid, makes a protein that's doing wrong function. And this wrong function of the protein is causing the cell to behave differently. It's having a grow signal. And of course, this cell itself and some other cells are surrounding and trying to fight against it and try to fix it. In most of the cases, fortunately, it's fixable and we are okay. But in the cases when it becomes not fixable, this cell grows out of control, grows into a big mass. That's the tumor. And that's caused one of the biggest health problems nowadays for the entire society. So everything comes down to just a few atoms, a few chemical bonds that's going wrong. And for me, in terms of understanding why we're having this disease and how we can fix them, how we can cure this disease, we really need to understand this molecular mechanism. And my favorite approach is I want to see how things are working when we're healthy, how things are going on when we have a disease. Because seeing is believing. Well, don't get me wrong, there are a lot of understandings that now we have in how the life going on. That's coming from very clever experiments, indirect observations, indirect perturbations, and logical thinking, and sometimes imagination. And we have learned a huge deal of that. But sometimes the evolution of life has chosen ways that's beyond logic and beyond imagination. And this is when a picture is worth 10,000 words. As you may remember, the cells are quite small and smaller than our hair. And seeing that structure with our naked eye is pretty much impossible. So we need to make things bigger. We need magnifier. We need microscopes. And that's dated back 400 years ago. And Janssen & Janssen, it's a Dutch father and son, invented the first compound microscope in the world that has a magnification of 9. So things become 9 times bigger. But you can see that exactly put the cell in the range that we can see with our eyes. And then later, there are improvements of microscope building, actually polishing the lens. And Leeuwenhoek, one of the famous lens polishers at that time, made a single lens microscope that has a magnification of 200 times. And in fact, if you have a chance to visit Bias Hall, 3rd floor, there's a replica of that microscope you can see on display. And there's a lot more we can see with that in better magnification. And well, I keep mentioning the name of a cell. This is a bad joke. You may also recall the cell in the prison that's knocking people up. And is there any connection between the two? Well, unfortunately, they meant pretty much the same thing. So there's a British scientist, Robert Hooke, puts the wood cork under the microscope and saw the honeycomb structure. That reminds him the cell that the mid-age monastery, the monks living in there. They say, oh, they look alike. So he named this honeycomb structure the cell. And that's why we call the fundamental unit of the cell. They meant exactly the same thing. And with this ability to see things, we can get lots of pleasant surprises knowing how things are going on for life. How about the inner world? Well, things are much smaller, and we're trying to, well, over these 100 years, people are trying to develop ways to improve the magnification of the microscope. Things become more and more complicated. You can get 1,000 times, 10,000 times magnification, but you don't see things better that's because of physics of light. The light is a wave, and they have a wavelength. The red light is about 600 nanometers wavelength. Green light about 100 green light is about 500 nanometer. And physics says that you cannot see things smaller than half the wavelength of light, which is exactly the subcellular level. And try to fight against the physics, you're doomed to fail. So over the past 10 years, we and other people have been trying to develop ways to get around physics. And there's some clever designs like giving the ability that we can see individual molecules and measure the position and picture together a structure based on the position of every single molecule in the structure. We can now push the resolution down to the size of a molecule. And that enables us to see a lot of fine details. For example, our collaboration with Jeremy has used these methods so that we can see how a mutation in Guillain-Barré syndrome is changing the structure of the cilium. On the other hand, we're also trying to push for seeing things bigger, seeing things in the context, not just the cell, but the tissue or the human body. And this is what we're going to do. There's not more challenges. In the end, you know what we're trying to do? We want to take a picture of the Earth from the universe. We want to see the stage, not just see the stage. We want to see my fingernail from a picture of the Earth. And this is what we want to push for. And I hope it will give us enormous new knowledge of what's going on. And someday, we'll be there. Thank you.
Thank you, Beau. Will you join me in giving all of our Discovery speakers a warm round of applause? I encourage those of you who have questions and comments to come to the front and talk with the speakers. You're free to stick around and mingle with each other. Thank you all for coming, and I hope you enjoy the rest of the weekend.